Okay, it looks like everybody's here. Thank you everybody for joining us today. My name is Vincent Britz, or Vince for short. I work at Flownex International in a development role as well as in a high-level technical support role as well. In today's webinar, we're going to be looking at one of the newest enhancements in Flownex. It is our automated drawing measurement tool. Essentially, it extends our scale drawing functionality and allows you to include measurements on these scale drawings and connect them to arbitrary inputs on components. Just before we get into the content of the webinar, I'd just like to explain what the software is and where it sort of fits into the simulation world, just in case anybody hasn't heard of it. Flownex itself is a commercial simulation software. It's essentially a 1D CFD code of sorts. We use conservation of mass, momentum, and energy, and essentially build a network out of one-dimensional flow and two-dimensional heat transfer components, and then solve that network using a pressure correction method, very similar to how a CFD solver would work. Due to the nature of the solver, the networks can be very generic. There's no limitations in how the components have to be connected, and essentially gives you very fast solutions. Unlike CFD, where you have turbulence models to account for pressure drops, for example, inside of Flownex, we use empirical correlations on top of these conservation equations to provide values for, say, wall shear stress terms or heat transfer coefficients, for example. All of these validated correlations are then used in conjunction with these fundamental governing equations and provide a sort of a 1D model of a system or of a component. Flownex itself is capable of both steady state and transient simulation. We use the same solver for both of them, so there's no need to worry about turning on the transient solver or turning on the steady state solver. They're essentially the same code. We have many different fluid types inside of the software. Obvious fluids of incompressible and compressible fluids. For all our secondary flow components, all our secondary flow system modeling components, we have full compressible theory applied there. So no incompressible assumptions in those components. And then also have a lot of other fluids available as well. These can be mixtures of gases and liquids, perhaps oil and air in a lubrication system, or perhaps a two-phase fluid like water where you have condensation and evaporation. The software itself is also built for customization by the users. So we have lots of options where the users can specify their own correlations. They can build their own components. This is especially useful for clients who consider their correlations part of their intellectual property and as a result hold onto the correlations. So having these customization options allows you to easily add these proprietary correlations into your simulations without having to share them with anybody else. The code itself is also designed within an NQA1, which is the Nuclear Quality Assurance, as well as an ISO 9001 environment, basically ensuring high standards of quality in the software development. When we looked particularly to the gas turbine industry, Flownex is very useful in the preliminary design stage. CFD solutions can be used in the design stage as well, but they're very, very time consuming in terms of setting up the models as well as solving the models. And as a result, they're typically used later on in the design stage to verify designs. In the early stages, network tools or 1D codes are typically used. And this is where Flownex really offers a lot to the industry. The software itself is useful in predicting flow rates, heat transfer, pressure drops, etc. And applications of the software in the gas turbine industry include combustor analysis. This is in predicting liner wall temperatures inside of combustors to work on cooling airflow distribution. In blade cooling modeling, where we look at modeling the internal flows inside of the turbine blades, looking at the internal heat transfer over the turbulators and throughout all of the components inside of a turbine blade. Secondary air system modeling, which we'll talk a bit about today. Lubrication systems, where you have basically bearing chambers which are pressurized with secondary air, and then have oil which flows through scavenge lines into reservoirs. Flownex is useful in modeling these systems. And then lastly, full integrated system models. We have the ability to model components like compressors or turbines in a very high level as well, using compressor charts or stage models. And what it basically allows you to do is to link your secondary air models or perhaps a lubrication model right to a full engine simulation, where you can adjust things like atmospheric boundary conditions and then have the boundary conditions of your subsystems calculated through the system components as well. All right, so in terms of secondary air modeling in 1D codes in general, these systems are incredibly geometry intensive. I have a small picture on the bottom right over here showing a couple of rotor discs that you'd see in this case a compressor stage or a turbine stage. A compressor in this case. But anyways, the geometry here is very complex, and to correctly model this flow, it's important to be able to put in the profiles of these walls to calculate windage, as well as the radial locations to ensure that any radius changes in the flows is correctly accounted for, along with all of the other traditional values like you would expect, like lengths or diameters. As a result, building these models requires a lot of geometric inputs, which are usually measured from CAD files quite manually. As great as it would be to have a full 3D importer for a CAD model, this is something that's very difficult to achieve in a practical sense. And essentially a lot of the work comes down to manual copying of measurements from CAD files into simulations. But in the design process of these systems, we often see many iterations. I mean, one of the benefits of using 1D codes in these simulations is the ability to have very fast solution times and do extensive parametric studies. This results in many updates to the geometry in the simulations and then even more manual work specifying these values. So in general, modifying the geometry in these models is very time consuming. There are lots of inputs. And then what's more important is once you've made a small change to the geometry or you have a revision on your design, you then have to ensure that every single input specified in the model is correct, has been updated. And that validation stage is incredibly important. Missing a change in radius for a component is not easily picked up and requires a very, very critical concentration by the engineer who's doing the simulation. So basically to address a lot of these challenges, we've been working on some additional enhancements to our scale drawing functionality to take these geometric inputs and link them directly to measurements on a drawing itself. So essentially trying to remove a lot of the manual work and then also create or sort of ease the validation stage where you can simply confirm that measurements are placed correctly on a drawing rather than clicking on every single component individually and checking the inputs against CAD measurements. So to demonstrate this functionality today, I'm going to use a simple secondary air model here. We have a compressor stage tapping. I've labeled that as inlet. We then have radial inward holes with some axial inclination angle into a rotating cavity. There are about 30 holes in parallel, essentially, around the circumference of the machine. This flow then goes through this first cavity, which is got rotors on both sides. So essentially a rotor-rotor cavity, through a small restriction into a second cavity, and then through to be used later on in the machine. Just for this simulation, we're going to stick with a very simple geometry so we can focus on the measurements. But just to reassure you, there are many rotating flow components in Flownex design and modeling, all of the features that you see in typical secondary flow systems. So we're keeping the example simple today just for sort of an easier to understand model rather than to showcase all the functionality of all the components. So in terms of the actual exercise, we're going to be looking at optimizing the geometry of this inlet hole or these inlet holes in terms of the diameter of the hole, in terms of the axial inclination as labeled alpha in this drawing, and then also the forward or back sloped angle. In this case, I've labeled it beta. We have some limitations on these values. Our angle for beta must be less than 30 degrees. This is basically limited by the geometry in the system. The axial inclination angle can't be less than 10 degrees or greater than 20 degrees. And the diameter of these holes must be less than 35 millimeters. So with those constraints, we can go ahead and optimize the angles for alpha and beta, and then optimize the diameter of these holes to provide a minimal pressure drop through the system. So we have a target mass flow rate of 20 kilograms per second, and we would like to maximize our outlet pressure by changing these geometric parameters. Okay, so I'm going to jump across into Flownex and just talk through how we would set up these scale drawings. If you're familiar with the software, you'll notice that in the latest release, there is a new ribbon at the top labeled scale drawings. This used to be a section under imports, but we've now moved it to a full ribbon on its own with a lot more functionality added to it. So just to explain how this all works, I'm going to create a scale drawing. So on the left here, we have generate scale drawing. If we click that and then choose an image. So here I'm going to have this image that was in the slides. For Flownex to add measurements to it, we need to add some reference points on the drawing. The way we've done that is through these colored boxes. So I'm going to add them at 2 locations in our drawing where I know the radial position and axial position. So I have these 2 locations. We need to give it a name. I'm just going to call this Flownex webinar. Our X position of our blue marker, I'm going to set as 0. This is essentially the axial measurement. The actual measurements in these systems are not crucial in terms of their reference point. The radial positions are obviously referenced to the central axis of the machine, but the axial reference point can be chosen by the user. So I'm just going to choose the left one as 0, and then the right axial location will just be 0 plus L in this case. If we go across to our slide, the length was 265 millimeters, so I'm just going to drop that in. We have the ability to specify this in most of your standard units, so you have the ability to put this in inches as well, or in meters, depending on what the dimensions in your drawings are. This image, by the way, is just a PNG. Flownex supports many different image formats as well, and you can add your own custom images just through a standard file selection dialog. So you're not limited to any particular file types other than, say, bitmaps, GIFs, JPEGs, and PNGs. So standard drawing formats. Then we need the Y locations for the markers. So the Y location here will represent the radial position. So in this case, R2 would be the Y location for the blue box. That is 470 millimeters. And then the other location would be 150 for the red box. So with that information, Flownex has enough data to fully scale this image in both X and Y. If we press OK right now, it'll jump across to the software, and now we have a background drawing which we can add our components on top of, which maintains its measurements according to the scale that we input, or those reference measurements we put in. So for example, I'm going to add a rotating cavity in the middle over here and specify some of the typical inputs we'd see. So a cavity needs an inner radius, an outer radius, and a shroud width. So for the outer radius, we can simply add a point measurement. So I'm just going to zoom in, click, and add a measurement over there. In the case of very lightly colored images like this, where we have light grays and light blues, it's not a problem to actually pinpoint the black markers on top of that. But in the case where you have hard black lines like CAD files, we've added an opacity slider so that you can just simply reduce the opacity of the drawing and see your measurements a lot easier. It's also possible then to completely hide the measurements or hide the components when you're actually working on the model, but I'll show you that in a minute. So we've added a location for the outer radial position of the cavity. I'm going to add a marker for the inner radial location, and then I'm going to add a measurement for the shroud width. So there we are. So if we click on these components, so first I'm going to start with the point measurement. Here we can see the Y value, which in this case would be the radial position. So we can see the outer radial value. Over here, we'll be able to see the length of that particular measurement. And then the same will apply at the bottom for our inner radial position. When it comes to linking these values to components, it's just as simple as dragging or dropping the value onto the measurement. So I'm going to link the outer radius value to that measurement. We want to assign it to the Y value, as the Y value here represents the radial coordinate. Once that's done, you'll see that that value has been transferred directly into the user input, and that value is now grayed out. Essentially, it's being completely controlled by that measurement. If you're ever interested in working out which measurement it's linked to, all you have to do is simply right-click on it and go to the disabler. That will be the component where the information is coming from and populating this user input. We can do the same for the inner radius by just simply dragging and dropping, and then the same for the shroud width by dropping onto the length. So in a couple quick measurements and then some dragging and dropping, we can specify a lot of the geometry of the cavity. What's really important about this is now we can move these coordinates, and all of the measurements will update. So I'm going to add the outer radius as well as the shroud width to the drawing canvas. And then as we go ahead and modify these measurements, you'll see that the values update. So here our shroud width is changing. And then if we go ahead and move the location of our measurement point, we see our outer radius value change as well. So these measurements are dynamically linked to the inputs, and as the measurement changes, the input changes accordingly. So if there are any changes in your design, you can go ahead and just simply reposition the measurements to match the new geometry that's in the background, and then Flownex will automatically update the inputs of all the components that are connected to those measurements. All right, okay, so in a practical sense, we're going to look at the optimization study. So for that, I've built the network earlier, just to keep the webinar relatively short. I don't want to spend too much time talking about adding all the components and specifying all the inputs. I've left a couple of inputs deliberately blank so that we can go ahead and specify it here, and then we can continue with the optimization study. So here I'm missing the shroud width and the outer radius, so I'm going to add some measurement points at the top of the drawing over here. Then I can link those points to get a length. It's possible to use the link points to get a length, or just simply to add a line measurement as well. I'm going to link these measurements to the inputs of this cavity. So just drag and drop the outer radius onto the measurement point and assign it. And then the same with the shroud width. On this cavity, the machine speed is also missing. In one of our recent updates, we also added the ability to use global parameters. So if you look on some of the other rotating components, like this rotor cavity, you'll see the machine speed is specified and the output is grayed out. This output is being specified in our global parameters window, and essentially is a single value that will populate multiple inputs in your model. To assign an input as a global parameter, all we need to do is type a $sign and then select the name of the global parameter. If the global parameter that you're looking to use hasn't been specified yet, you just simply need to type a name for it. So this could be, say, var1, and then that will be added to the list of parameters. Once the parameters have been added, you can simply just select that parameter, and that value will be copied into the input automatically. Changing the value in one place will then also update the value in all the other locations. So it's not necessary to set up complex parametric tables just to control the RPM. All you need to do is just specify a single machine speed. Changing it on one component will change it on all of them. Okay, so in terms of setting up the optimization here, what we need to do, as I mentioned in the introduction, is to look at the angle alpha, the forward or backswept angle beta, and then also the diameter of this channel. Just to assist in some of the geometry, I've added a simple script over here. It just manages some basic trigonometry for calculating the length of the channel as this angle alpha and beta changes. If this was a Um, if this channel was going to be a fixed size and we weren't going to change it through a parametric study, we could go ahead and add measurements to the drawing and then link those measurements directly to the inputs. But since in this sense we're trying to change these parameters, I've gone ahead and done some simple trigonometry calculations and put them in the script and linked them to the inputs on the component so that it can calculate the length as we change these component inputs. And update the component, as we change the parametric study inputs, and then update the component inputs that follow. To actually go ahead and optimize the system or to understand the effects of all of our variables, I've created a parametric table. Each of the columns in this parametric table represents a different variable inside of the simulation. So this column represents the value for alpha, then the value for beta, and then the diameter. Each row represents a different case in the parametric study. You can see here we have 27 different cases showing all of the different tests. Essentially, I'm testing for a variation in the alpha angle of 10 degrees, 15 degrees, and 20 degrees. The angle beta is tested at -20, -25, and -30. The minus here indicates a backswept angle. I'll explain that in a minute as to why that's important. And then just varying the diameter between 27 and 33 millimeters. To actually solve this, it's just as simple as activating that parameter table in our sensitivity analysis. We can go across to a results page where I've basically extracting all the results from the runs and then graphing them inside of an Excel environment. If we now run our sensitivity analysis, Flownex will read each line of that parametric table, change the inputs in the simulation, read the results, and add them line by line in this Excel report. These Excel graphs are then just dynamically updating to the values that you see in these rows. So if we look on the left here, the way I chose to lay this out was to have the angle alpha plotted across 3 different graphs, to then have the angle beta plotted as 3 different lines, and then have the diameter vary on the x-axis. So right off the bat, we can see that in all cases, or all angles for alpha, the green line, or this greenish yellow line, is on top, basically indicating the highest outlet pressure and therefore lowest pressure drop. This is for a backswept angle of -30 degrees. Next, we can look at the angle alpha. In this case, we have 10 degrees. That would be the lowest axial inclination angle, or this lowest angle of alpha. As this angle is made larger, the radial component decreases and the axial component increases. But as a result, the length of this channel also increases. So as alpha is smaller, this channel is smaller, and as alpha is larger, the channel is larger. That essentially results in increased frictional losses as the length of these rotating channels is higher. So if we look across at the results from our parametric study, we can see that for smaller angles of alpha, we see higher outlet pressures. If you look closely at the graphs, you'll notice that the points progressively get lower as we progress through through the parametric study, looking at the deviation in the angle alpha. This is a very small change, but essentially an angle of about 10 degrees for alpha and 30 degrees for beta are ideal values. In terms of diameter, we see quite a large difference between 27 millimeters and 30 millimeters, and then a small change up to 33 millimeters. To refine the parametric study and to look at the effect of the diameter in more detail, I've created a second parameter table where I'm varying just the channel diameter and keeping all the other parameters constant. So I'm just going to enable that parametric study, disable the first one, and here you can see we just have the value for alpha set at 10, beta at -30, and then varying the channel diameter from 27 to 35, this time in increments of 1 millimeter. We can now change the sensitivity analysis to run the second parameter table and then run our sensitivity analysis. Here we can actually see the precise change in outlet pressure with diameter, and hopefully hone in on a very specific diameter to use for our compressor tapping holes. Looking at the results, you see at about 32 millimeters, about here on our graph, we get our maximum outlet pressure. and this can essentially be passed on to a team in terms of the preliminary design for these compressor tapping holes. In terms of the theory and as to why these values are ideal, it's best to look at the swirl ratio distribution inside of this cavity. The reason for that is the pressure drop through these rotating channels is really just a function of the velocity and the length of the channel. The pressure drops in the remaining part of the system are actually relatively minor compared to this large radial change, and then the vortex pressure drop through this first cavity. But this angle alpha and particularly the angle beta have a really large effect on the swirl ratio distribution in this very first cavity. So I've prepared a slide that just discusses this in a bit more detail so we can understand the results that we're getting from our sensitivity analysis. The first thing that you'll notice on the left here is I have plotted the swirl ratio. This is the tangential velocity of the flow or of the air divided by the tangential velocity of the machine. So a number 1 would mean that the air and the machine are rotating at the same speed. A swirl ratio of 4 would mean that the air is rotating 4 times faster than the machine. This is for the case where there is no forward or backswept angle, so beta is 0, and this is for the case where the backswept angle is minus 30 degrees. In both cases, you'll notice that as we move radially inward through our cavity, we see an increase in the swirl ratio. The air that enters the cavity has a fair amount of angular momentum, and as that air is forced to travel radially inward, we see its tangential velocity increase as a result. You notice that in both cavities where an inward flow in our radial direction results in quite a large increase in our swirl ratio. When we look at the actual results from these simulations, we see that for a hole that has no forward or backswept angle, we see an outlet pressure of about 864 kilopascals, whereas for a case where we have a backswept angle of 30 degrees, we see an outlet pressure of 1,126 kilopascals. This can be attributed to 2 factors. The first one being the minor contribution from the windage. The windage is essentially the power transfer between the air and the machine itself. A positive windage will indicate that the flow is doing work on the machine, and a negative windage will indicate that the machine is doing work on the flow, just following a thermodynamic convention. Here we can see that for the cavity, the air is rotating faster than the machine, and as a result, we're doing the flow is essentially trying to accelerate the machine, and we see quite a large windage of about 4.1 kilowatts. Whereas in the case where we have a large backswept angle, the flow that enters this cavity is in the opposite direction to the machine speed, and as a result, the angular velocity of the air in the cavity is much lower than the machine speed. It's not negative because there is still friction on the walls in the cavity, which tries to accelerate the flow in the direction that the machine is rotating, but the backswept angles, along with the velocity of the flow at the inlet, results in a reduction in the swirl ratio. So here you see at the inlet of the flow, we see a swirl ratio of about 0.3, increasing up to a swirl ratio of about 1.3 at the outlet. The most important factor and the actual physics that results in a much lower pressure drop for the backswept angle compared to the hole with no backswept angle is essentially the way in which the pressure changes in a vortex. This equation at the bottom here, if you're familiar, is the change in total absolute pressure inside of a forced vortex. So beta here is the swirl ratio, omega is the machine speed, rho is the density, R2 and R1 are the radial locations that correspond with P2 and P1. In this case over here, you can see that as the value for beta increases and decreases, this pressure drop changes according to this beta value squared. So in this case over here, if we were to find the average swirl ratio for this cavity, it could perhaps be 0.8, while in this cavity over here, our average swirl ratio may be 2.5 or even 3. This value squared will have an impact on the pressure, whereas a lower value over here results in a much lower pressure drop due to the radius change inside of that vortex that's formed inside of the rotating cavity. Looking at the results like this, especially looking at the swirl ratio, really helps to understand why the sensitivity analysis is showing that large angles or large backswept angles produce lower pressure drops. You might also think that a smaller backswept angle and a higher exit velocity would have the same effect. Essentially, the higher exit velocity and the lower backswept angle may contribute essentially the same tangential velocity at the end of the cavity, but in reality, that higher velocity results in a higher pressure drop in the compressor tapping holes, the radial inward holes, and the pressure drop increases with the square of the velocity, whereas the length increase from changing the degree to which we backsweep the holes only increases with a linear relationship. So the length of the channel increases the pressure drop linearly, while the velocity in the channel increases the pressure drop by an exponent of 2. All right. Okay. So enough about the theory. If we then consider quite a practical scenario in a design setup, let's say that we found the optimal sizing for these compressor tapping holes, and we pass this information on, and there's a design revision that results in the diameter of the shaft changing. So in this case, our shaft diameter is about 150 millimeters. If there was a design change that made the shaft larger, we'd have to go and update a lot of the geometry inside of our model, particularly the inner radius of our cavities, and then from there we'd have to recompute our sensitivity analysis and try and find a new optimal size for our compressor tapping holes. So the way in which you can do this with the scale drawings is simply by clicking the Change Drawing button, and then we can select an updated image. So here I just have a similar image where I've just modified the geometry slightly. The inner radial location, instead of being 150, is now 180 millimeters. And I just have to move these little markers to indicate the positions to which I'm using these reference coordinates. Let's just move it to there. Okay. Now Flownex will rescale the drawing. You can see that some of the components are now misaligned on the drawing canvas. Some of our measurements are no longer on the correct locations. All of this would represent geometry that would need to be updated when you do a design revision. So what we all need to do, or what we simply need to do in this case, is just move the geometry or move the location of the measurements. So all I'm doing is moving the measurements to the points where they would line up with the drawing once again. Okay. So very simply, I'm able to change the measurements in our drawing. Just go ahead and do that. As I mentioned earlier, these measurements are dynamically linked to the inputs. So if we click on the cavities, we'll see the inner radius has been updated. It was 150 millimeters earlier. Now it's been changed to approximately 180 millimeters. And just like that, we can do a simple update of the geometry inside of our system by replacing the background picture and then just realigning the measurements. So it provides a very convenient way of re-specifying the geometry, and at the same time provides peace of mind that all of the inputs have been updated. We can very easily look at the image, perhaps hide the flow components if needed, and look that all of the measurements are at their correct locations in terms of the new geometry that's been specified. We can then go ahead and rerun our parametric study. If we remember from earlier, our previous optimal diameter was 32 millimeters. So I'm going to go ahead and rerun the study, first looking at the effect of alpha and beta, just to ensure that there's been no change there. So let's change our sensitivity analysis. Let's switch back to the first parameter table and then run our sensitivity analysis. So again, it will consider all 27 cases with the updated cavity geometry that resulted from a change in the shaft diameter. So if we just give this a few seconds, it should be done. Every single one of these is a steady state solution. The simulation time here is about 1 second. This is running on a sort of a consumer grade laptop. For larger secondary flow networks, we're going to see solving times typically under 10 seconds, even for relatively large networks. So the simulation is finished, or the parametric study is finished. As from before, we can see that for angles of beta, minus 30 degrees is still the preferred angle. For angles of alpha, 10 degrees still appears to be the best value. As I mentioned earlier, this is having an effect on the length of the channel. So we see a very small change in the outlet pressure with the change in alpha. And then diameter, this time now we see quite a large change between the 30 millimeter hole and the 33 millimeter hole. But again, we can switch across to our second parametric study and then look at the effects of the diameter in a bit more detail. So I'm going to run that second parametric study again. Just before, if you remember, the optimal value was about 32 millimeters. We can rerun this parametric study. Again, it's keeping the value of alpha and beta at 10 degrees and minus 30 degrees respectively. And now in this particular case, we see an optimal size of our hole changing from 32 millimeters to about 34 millimeters. So if we go back to the image, essentially by reducing the radius of by increasing the radius of the shaft, we've decreased the radius change between the exit of this radial inlet hole and the point where the flow exits this first cavity. That decrease in radius has resulted in a change in the total swirl ratio that goes across the cavity. So essentially the point where we see the velocity exiting this hole being ideal has now shifted from a diameter of 32 millimeters to a diameter of about 34 millimeters. We can then pass this information along again as the ideal values for our compressor tapping hole geometry, and then use that in any further design iterations. Okay, so basically to summarize the contents of the presentation, this updated scale drawing functionality, these enhancements to the scale drawings, now provide engineers with a convenient specification of geometric inputs. This is particularly relevant in secondary flow modeling, where a lot of geometry is required for these systems, but can also be used in any other Flownex model. These measurement tools are not limited to the rotating flow components and can be used with any components in Flownex, be it pipes, cavities, or even pumps, for example. Anything that could have an input can be directly linked to a measurement on the canvas. These inputs, or these measurement inputs, also provide an easy way to validate the geometric inputs of your model after a geometry change. So like the second scenario where I changed the image in the background and then moved the location of the measurements, you can do this in a geometry change inside of a system. Perhaps the size of a labyrinth seal changes, or the radial location of a labyrinth seal changes, or the profile of a rotor stator changes, or something like that. All of this information can be captured in drawings. The drawings can be updated, and then the geometric inputs will be updated automatically. Lastly, it also makes it possible for us to reuse our parametric studies. So in the first iteration, I set up a parametric study and was able to reuse the same parametric study in the second iteration. Often, if you would have quite a large change in the geometry of your system, it might almost be more convenient to insert the components again from scratch to ensure that you don't forget to change an input. by linking the inputs directly to geometry, you can be confident that all the inputs will be changed, and then you can safely reuse models. So in summary, Flownex provides engineers with a user-friendly environment where you can specify the inputs for your secondary flow models. And these models produce accurate results with fast computation times. So it allows you to do extensive parametric studies for the optimization of the flow in these systems, and then also gives you peace of mind when it comes to the inputs and design revisions through these systems. All right, thank you very much for your time. If you are new to Flownex and would like to give the software a try, please feel free to contact us. We've got an email address over there, sales@flownex.com, and then a website as well. You can simply complete a contact us request on the website, or alternatively just send us an email. We'd be more than happy to explain the particular applications that will be relevant to your company and discuss how Flownex can benefit you. We do offer evaluations or trials as well for the software, and we have channel partners all across the globe which would be happy to meet you and assist you in person as well.